Welcome to today's Trane Engineers Newsletter Live program. I'm Jeannie Harshaw, and today we're going to continue the conversation on decarbonization and the electrification of heat. Now, we've been talking about these topics for a long time. In past programs, we've discussed what decarbonization is, how systems and equipment can be designed with a lower emissions impact, and we've spent considerable time on a variety of electrification of heat topics. Now, we're going to focus on something a little different, the economic and emissions impacts of these decisions. Many decarbonization decisions must be balanced with customer requirements, operating costs, first costs, and emissions. Today, we're going to review how the electrical grid operates. We're also going to look at different utility rates and how these might impact projects. And finally, we're going to pull it all together with an example where we will evaluate different upgrade scenarios and review the economic and emission impacts. To cover today's topic, we have application engineers Michelle Hull and Eric Sturm, and they're joined by Emma Van Fossen, a Trane energy engineer. Emma's going to start us with a review of the electrical grid.
We're starting this E&L by providing some context on how the electrical grid functions in order to explain why utility rates and emissions factors are the way they are. Electrical grids are complex, and a lot of that complexity arises from the fact that there are many different energy resources that utilities use to generate electricity, each of which behaves differently and comes with unique challenges. This slide shows the percentage that the most common utility-scale electricity generation resources contributed to total generation in the United States in 2023. It's based on data from the U.S. Environmental Protection Agency's Emissions and Generation Resource Integrated Database, or EGRID. These numbers reflect the total across the entire year, but keep in mind that the resources that are actively generating electricity for a grid, or online, are subject to change throughout any given time period. Let's use this time series chart published by the Electric Reliability Council of Texas, or ERCOT, as an example to illustrate the transient nature of electricity generation. The chart shows instantaneous electricity generation measured in megawatts over the course of a day, starting at midnight on April 1st, 2025, and continuing to midnight April 2nd. The grid started out with nuclear, coal, natural gas, and wind power generation. At about 6 in the morning, the grid needed to increase generation to meet the demand of consumers beginning their day, and this increase was accomplished primarily by bringing additional natural gas generation online, as well as some stored power. When the sun rose between 7 and 8 in the morning, solar generation joined the mix and allowed the utilities to decrease natural gas and stored energy power. Solar production began to decline rapidly shortly before 6 p.m. or hour 18, requiring other resources to come online to replace that generation output. Again, this was accomplished primarily by bringing additional natural gas generation and stored energy online. Demand began to decrease slowly between 8 and 9 in the evening, or hours 20 and 21, and wind production began to increase around the same time. Both of these factors allowed the utilities to decrease natural gas and energy storage power production. This example shows how the electricity generation mix is constantly changing as resources are brought on and offline in response to demand and weather conditions. The generation output of some resources varies quite a bit throughout the day, while for others it stays nearly constant. Aside from electricity generators, I want to discuss a few other resources that interact with the grid. First, electricity storage. We saw in the previous example that the ERCOT grid used stored energy to meet demand peaks when solar energy was not available. Energy storage technologies such as batteries don't generate electricity, but they make certain generation resources easier for utilities to use. We'll explore that concept more shortly. Another important concept is distributed energy resources, or DERs. Definitions vary, but in the broadest sense, DERs are resources that interact with the grid, but are not owned or operated by the utility itself. Some DERs do generate and send electricity onto the grid, such as rooftop solar panels on residential and commercial buildings, privately owned wind turbines, and combined heat and power or CHP plants. By some definitions, resources that do not generate electricity can also be considered DERs. Electricity-consuming devices impact the grid by affecting the amount of load that must be met. Large electricity consumers with the capability to be remotely controlled are often considered DERs because they can be used to reduce the total load on the grid during high demand times, mitigating the need to bring additional generating resources online. Many utilities have demand response programs for this purpose. Examples of significant consumption-based DERs include electric vehicles, especially electric vehicle fleets, building-scale energy storage, such as batteries or ice tanks, and even building automation systems and building HVAC systems, which can use control strategies to significantly reduce building load during high-demand times. One final concept to discuss is virtual power plants. This is a fairly new concept that refers to the aggregation and coordination of DERs into a resource that can be dispatched by grid operators. Now that we've introduced the major grid resources, let's discuss three of the most important concepts characterizing these resources: firmness, dispatchability, and emissions intensity. The first characteristic is firmness. Firmness refers to the extent to which the amount of generation can be predicted in advance. For example, wind and solar both depend on weather patterns that cannot be predicted exactly, so they are intermittent or not firm. However, resources like nuclear and coal produce an exact amount of output electricity per input, so they are very firm. As we discussed, energy storage such as batteries are important grid resources even though they don't generate electricity. An intermittent resource paired with energy storage acts as a firm supply of energy. So, for example, while solar generation itself is intermittent, if solar energy is produced and then stored in batteries, that power is firm. However, batteries differ from other firm resources in that they're not viable for very long-term storage. Whereas coal or natural gas can technically be stored indefinitely, battery energy can't due to self-discharge and loss of capacity over lifetime. Similarly, pumped hydro, which is a form of energy storage, is more firm than run-of-river hydro because pumped hydro plants can maintain more consistent water levels and thus generation capacity. There are some nuances to firmness. For example, biomass plant firmness depends on the biomass feedstock, so this graphic should be interpreted directionally and not as an absolute statement. Another characteristic is dispatchability, which refers to how quickly and easily a resource can be brought online. A highly dispatchable resource can quickly be brought online, whereas a non-dispatchable resource takes longer to start generating electricity. Dispatchability and firmness are interrelated. Sources like wind and solar are non-dispatchable for the same reason that they're not firm. They can't be turned on at will because they depend on weather conditions. Other sources, such as nuclear, are non-dispatchable because of the long startup times. The term load following is used for dispatchable sources because they can be brought on or offline to match generation to the load on the grid at any given time. Energy storage, especially batteries, are highly dispatchable. Similar to how energy storage makes the power produced by intermittent resources firm, it can essentially make energy generated from non-dispatchable sources dispatchable. In fact, batteries offer the quickest dispatch times, typically a fraction of a second, whereas most other sources considered dispatchable are on the order of minutes. There are also nuances to dispatchability. For example, nuclear and combined cycle plants can have either a cold startup, which takes longer, or a hot startup, which is relatively quicker. There can be a wide range of startup times for some sources, depending on the plant design. The final characteristic of electricity generators that we'll discuss in this session is operational emissions intensity. Operational emissions are the greenhouse gases that are produced while the source is actively generating electricity. Higher operational emissions intensity, or dirtier sources, produce more greenhouse gas emissions per unit of electricity generated, while cleaner sources produce fewer emissions per unit of electricity. Some sources have a wider range of emissions intensity than others. For example, biomass emissions intensity can vary greatly depending on the feedstock, although in practice, some emissions factor references effectively treat biomass generation as carbon neutral because biomass feedstocks sequester carbon during their growth period. Now that we know the basic characteristics of energy generation resources, let's explore how those factors impact how and why various resources are used on a grid. There are two concepts that will help demonstrate the operational impacts of resource characteristics: capacity factor and baseload versus non-baseload designation. Capacity factors describe how much electricity a source has actually generated relative to theoretical total possible production. As we see in this chart, based on electricity generation data from the U.S. Energy Information Administration from 2022 through 2024, there's a wide spread in capacity factors for different generation sources. As we break down this chart, keep in mind that the trend shown for each resource includes all utility power plants that use the resource, and in some cases, there may be significant variance in the capacity factors for different plants using the same resource. Notice that intermittent resources, such as solar, wind, and hydro, tend to have lower capacity factors. These resources are generating only some of the time when the weather conditions are right, and so they have lower capacity factors than sources that can generate around the clock. This presents a challenge to grid operators who must ensure that they have enough generation capacity to meet forecasted demand. We will discuss consumer cost impacts of this challenge later in the ENL. Notice also that non-dispatchable resources, such as nuclear plants and natural gas combined cycle plants, have higher capacity factors. Remember, non-dispatchable resources can't easily be turned on and off, and so utilities tend to size them for minimum load so that they can run almost all the time. A power plant that's intended to run almost all the time, meeting minimum grid load, is called a baseload plant. Some resources that are dispatchable are still often used for baseload generation, such as geothermal and biomass. As you might expect, a non-baseload plant is the opposite of a baseload plant. It's designed to generate only part of the time. More specifically, non-baseload plants are used to generate in relatively short intervals to meet demand peaks. Non-baseload plants must be dispatchable so that they can quickly be brought online to meet peaks, and firm so that utilities can be sure that they will produce enough to meet the peak. So as you can see, natural gas turbines have a low capacity factor because they are designed to be non-baseload resources. Coal plants can be designed either to be baseload or non-baseload. The EIA publishes data for all coal plants in aggregate, and so coal has a mid-range capacity factor in this graphic because the capacity factors of both baseload and non-baseload coal plants are included in the same trend. Baseload versus non-baseload is an especially important distinction when considering emissions factors, and you can quickly deduce why when considering which resources are used for non-baseload generation. This slide shows the percentage that each utility generation resource contributed to non-baseload generation in the U.S. in 2023. The U.S. EIA considers power plants with lower than 20% capacity factor as non-baseload, plants with a capacity factor of 80% or higher as baseload, and plants with a capacity factor between 20 to 80% as partially baseload when tabulating emissions and calculating emissions factors. In this case, capacity factor is used as a proxy for dispatch order, since resources used only to meet peaks will have the lowest capacity factors. Recalling the operational emissions intensity characteristic, it's clear that the non-baseload generation is skewed towards more emissions-intensive or dirtier resources. Note that the EIA does not consider energy storage when considering whether a resource provides baseload or non-baseload electricity. As we discussed, battery storage can essentially make power from generation sources firm and dispatchable, and thus it can act as a non-baseload resource. As utility energy storage infrastructure expands, there's a possibility that it will make non-baseload electricity less emissions intensive. With generation sources constantly coming on and offline, determining electricity emissions rates, also called emissions factors, is complicated. For inventorying the emissions associated with electricity consumption, many organizations use annual average emissions factors across all generation sources used in the year. The EPA's eGrid database provides a great example of annual average electricity emissions factors. This map shows the average greenhouse gas emissions intensity of regions of the U.S. over 2023. The metric shown is total greenhouse gas emissions in units of pounds of CO2 equivalent per megawatt hour of electricity generated. CO2 equivalent, or CO2e, expresses warming impact of all greenhouse gases combined in terms of carbon dioxide. As we know from our capacity factor discussion, those sources can be broken down into baseload and non-baseload sources, and this distinction can make quite a difference in emissions intensity. Non-baseload emissions rates are also called marginal emissions rates, and they're helpful to assess impacts of changing load on the grid. For example, if we implemented a fuel switching project to convert load that had previously been served by on-site fossil fuels, such as a natural gas burning boiler, to load served by electricity, that is net new load on the grid. Remember, baseload generation resources are typically sized to meet the minimum load that the grid sees, so net new load added will be served by non-baseload resources. For this reason, the EPA recommends using non-baseload emissions factors to assess the impact of projects that will change electrical demand. All of these characteristics of electricity generation sources are important, but what most end consumers care most about is the cost impact of these characteristics. Now that you understand what's going on with generation of electricity, Michelle will explain its pricing.
Equally important to how our electricity is sourced is how much it costs. When determining if a project should use electrified heating equipment over natural gas heating equipment, one should consider comparing the operating costs of both methods. Even if a building is on an electric grid with a low emissions intensity, not many building owners have an unlimited budget. We can use the rate ratio for this analysis. The rate ratio is the ratio between the wholesale market price of electricity and the cost of natural gas, both in dollars per kilowatt hour. This is a chart of energy rates and rate ratios in the US, with each state listed on the horizontal axis. The dark blue bars represent the average electricity rate, and the red bars represent the average natural gas rate per state in dollars per kWh, as shown on the primary vertical axis. The light blue line is the rate ratio for each state, corresponding to the secondary vertical axis, which is unitless. The average rate ratio in the United States is 3.6, and each state's average rate ratio varies from 2.2 to 6.8. The higher the rate ratio, the greater the difference between the price of electricity and the price of natural gas. Rate ratios provide a general view that can help with preliminary electrification and decarbonization decisions. A building on an electric grid with a very low emissions in an area with a very low rate ratio would be an ideal place to consider electrifying equipment to decarbonize. A building on an electric grid with very high emissions, with no plan on decreasing those emissions, in a place with a very high rate ratio, would be the least ideal to electrify heating equipment if the goal were to decarbonize. However, a realistic example is somewhere in the middle. In the last graph of emissions intensity, we saw that Vermont currently has the fourth lowest emissions rates of all the states. Here, we can see the average electricity rate in Vermont is $0.1753 per kWh, and the average natural gas rate is $0.0256 per kWh. 0.1753 divided by 0.0256 gives us a rate ratio of 6.8, the highest of the states, meaning the price of electricity is much greater than the price of natural gas when compared to other states. This does not mean building owners in Vermont should not electrify heating. It all depends on the prioritization of decarbonization, heating equipment efficiency, and when and how much heating electricity is needed. The average wholesale electric power price is not a constant value, which makes understanding the utility rate in your area crucial. There are many ways utility rate companies can structure charges for energy sources such as electricity or natural gas, and they don't often clearly explain how rates are calculated on the bill. It may be tempting to take the total kilowatt hours and divide by the total costs on the utility bill, and conclude that electricity costs X cents per kilowatt hour. This is called a blended rate, which we saw used in the rate ratio equation. While this is simple to do and can provide a high-level price comparison, it is not accurate to use this value to determine analysis, such as equipment energy costs or payback calculations. This is because utility rates are not usually just one flat rate. There are types of charges, energy consumption and demand. Those charges are structured into different types of rates, such as flat, time of use, stepped, seasonal, or ratchet rates. Demand charges are assessed in dollars per instantaneous energy use. For electricity, this is measured in kilowatts. Energy consumption is the amount of energy used or consumed. For electricity, we measure this in kWh. To visualize this, we can plot the instantaneous electrical energy use, our demand, in kW over time. The consumption in kWh is equal to the area under the demand curve. Demand charges can be further broken down into either utility or grid demand charges. Utility demand charges generally monitor kW usage over 15 to 30-minute windows, then take the average during that window as one data point. For a given hour, the highest 15-minute window average becomes the peak kW for that hour. Over 24 hours, the highest hour is used as the daily peak kW. The highest daily peak kW over a 30-day period is then the peak demand for that month. A relatively short spike in energy use can impact the costs for an entire month, and in some cases, even longer. In deregulated markets, there's another type of demand charge called a grid demand charge. Often referred to as a capacity charge, it is the result of fees that power transmission operators charge the utility companies that generate the electricity to cover the costs of ensuring there is enough generation capacity to meet the peak electricity demand of consumers. You could compare the transmission operators to insurance providers for electricity generation to all the utilities in their area. Like utility demand charges, capacity charges are tied to peak kW. These power transmission companies work with utilities to determine how much peak demand will be needed on the utility grid for the next year. The power transmission companies then secure that much power, plus a safety factor, usually about 20%, in advance. These costs are then propagated back to the consumers. So what happens if the demand outweighs the supply? Over the years, demand increased considerably due to factors such as data centers and electrification of heating, while supply has decreased due to a combination of nuclear and coal power plants being taken offline and an increase in renewable energy sources, which have lower capacity factors. Recall earlier in this presentation, Emma talked about firmness, dispatchability, and capacity factors. She highlighted that the sources with a lower capacity factor, such as solar, wind, and hydroelectric, generate less electricity and are more difficult to use on the grid, so more resources are needed to generate enough electricity to meet consumer demands. The higher demand is versus supply, the higher the capacity charges will be. For example, see this table taken from the 2025-2026 Base Residual Auction Report for the transmission company PJM Interconnection. The total cost to load for PJM went from a total of $2.2 billion in 2024-2025 to $14.7 billion for 2025-2026. Which zone within PJM's region the building is in, and how much electricity a building uses during the demand peak will determine how much more per kW that electricity will cost, which could be as much as $151,000 per megawatt of capacity. Unlike utility demand charges, where the increased cost is due to the peak only you directly caused during the building period, the increase in capacity charges are because of that entire grid's peak electricity use. As Emma mentioned in the discussion about distributed energy resources, some utility companies have demand response programs that pay customers to curtail load during grid peak times to try to lessen the strain on the grid. This is a great way to incentivize consumers to lessen the grid's yearly peak demand for future years. But it doesn't change the fact that the money already used to secure power generation up front still needs to be paid back by the consumer, and it will be integrated into the utility company's rate structure for the next year. So, how are demand and consumption rates structured? For simplicity, the following examples will be for electricity, but note that any utility rate could use these structures. Flat rates, also called fixed rates, are a fixed price per unit. If you had a one-year contract with your local utility company that offered a fixed rate, the price per kWh would stay the same for that entire year. Time of use rates vary the cost of electricity depending on the time the electricity is consumed. This is usually categorized into on-peak and off-peak periods. The rates may vary by the time of day of the week, and by season. On-peak for a specific utility may be 3 p.m. to 8 p.m. on weekdays, with off-peak for all other hours. Stepped rates vary the cost of electricity depending on the amount of electricity used. The shape of the rate graph is the same as the name implies, and can either increase or decrease as the kWh increases. In this example, the rate is 12 cents per kWh for the first 3,000 kWh. Then 10 cents per kWh until a total of 10,000 kWh is met, 8 cents per kWh until 100,000 kWh, then all remaining kWh are 6 cents per kWh. Ratchet rates use a percentage of the highest peak over a specified period of time to set the minimum rate for the rest of the billing period. For example, a utility company could take your peak monthly kW from the year 2023, then set the minimum rate for the next year, 2024, to be 60% of the previous year's peak electricity use. Even if you barely used any electricity all year, but for 1 month used a lot of electricity, now you will have to pay for 60% of that peak as the minimum monthly charge for the rest of the next year. One utility may use a combination of multiple rate structures. For example, a stepped time of use rate with a flat monthly minimum charge. To further complicate things, utilities may also have other additional charges. These could include distribution charges, fuel charge adjustments, customer or service charges, power factor adjustments, efficiency credits, taxes, or fees. With all these charges, we can see why simply taking the total monthly charge on a utility bill and dividing by the total kWh or kBTU is not accurate.
Now, let's take these concepts and put them to use with an example. We'll look at this from both an economic and emissions perspective. We used an example 2-story office building that's served by an older system with components that need to be upgraded. The existing system features several multiple-zone VAB air handlers. The air handlers have some life left in them, so they're not going to be replaced. Conditioned air from the air handlers is delivered to VAB boxes. The perimeter VAB boxes have hot water coils to provide heat. The VAB boxes don't need to be replaced either, so the airside system could stay in place. The central plant includes 2 air-cooled scroll chillers, which produce chilled water for the air handler cooling coils, and a natural gas boiler to produce hot water for heating. Both the chillers and the boiler are due for replacement. The first thing we need to do is establish a baseline for comparison. Now, in this case, some of the equipment will be replaced no matter what. So our baseline is to simply replace equipment like for like. That means we'd install new air-cooled chillers and a new boiler. This baseline does represent a cost, too. There's the cost of new equipment, the cost of removing the old equipment, and the cost of installing the replacement equipment. Now, to perform this analysis, we use Trace 3D Plus to estimate the annual building energy use, utility costs, and CO2e. Trace is a whole building load design and energy software program that allows us to look at different HVAC configurations and calculate their expected energy use, cost, and emissions. A spreadsheet-based pro forma allows us to make financial projections, and this was used for the life cycle cost analysis. Now, the numbers we've used in our economic analysis might not look right for your market. Don't worry about that too much, because you need to perform this process for your building, your climate, market, and economics. Michelle has the details on the utility rate.
In this analysis, we're going to evaluate different utility rates to illustrate how rate ratios and how those rates are structured can affect the project numbers. We have a high rate ratio example, where the difference between electricity and natural gas is high, and we have a low rate ratio example. Let's start there, the low rate ratio, where the cost difference between electricity and natural gas is small. Here's our time of use utility rate. During summer on peak, our client pays 9 cents per kilowatt hour and $10 per kilowatt. During the off-peak summer period, they pay 4 cents per kilowatt hour and $10 per kilowatt. During the winter time, there is a reduction in on-peak, off-peak, and demand charges. Finally, our client pays 90 cents per therm for natural gas. This results in a rate ratio of 2.6.
So, we have an existing system that requires some equipment to be replaced, but the client wishes to decarbonize and reduce emissions as they upgrade. The baseline doesn't necessarily do this, so let's evaluate some alternatives. The first alternative is to replace the air-cooled chillers with similar models and remove the natural gas boiler. Removing the natural gas boiler should reduce the site emissions, but with the boiler being removed, we need a new source of heat. One option is to replace the existing hydronic reheat VEV boxes with boxes that include modulating silicon-controlled rectifier, or SCR, electric heaters. But we still have hydronic preheat coils in each air handling unit to deal with. This coil allows us to perform supply air tempering during the heating season when the mixer temperature is below the discharge air temperature set point. This could be electrified with modulating SCR heat. So let's look at the 15-year cash flow analysis comparing this first alternative to the baseline. Across the vertical axis, you can see money ranging from positive $600,000 to negative $600,000. The horizontal axis is time in years. Shown first, we have the fossil fuel cost savings in red. There's no natural gas use in this electrified alternative, so that's a positive value because it's an avoided cost. Next, we have electrical consumption and demand increases in blue and dark blue, respectively. These are negative values because our electrified alternative has more electrical consumption and demand than our baseline. To install the new chiller and VAV boxes with electric heaters, we have a first cost, shown here as project capital cost in gray. This is a negative cost, nearly $600,000 spent in year one. We need to account for the cost of the baseline, where we replace equipment like for like. This is represented as capital avoidance in-kind replacement in the hatched bar. This represents the money that would have been spent on the baseline solution to replace the end-of-life system with the same equipment. So when we're evaluating options for this project, we're comparing against the in-kind replacement to accurately represent the relative costs and benefits of each solution. This capital avoidance component allows us to compare against the true baseline. Finally, we have the cumulative cash flow line in black. This is the running total of expenses plus income. In our case, income is avoided costs through savings. Here, the cash flow starts in the negative, indicating the alternative investment cost exceeds the baseline investment cost. Said another way, our project capital cost exceeds the capital avoidance cost. And the cumulative cash flow line is sloped downward, growing negative over time, which indicates this alternative will not pay back compared to the baseline. With our current economic parameters and utility rates, this is not a good investment. It's important to talk about equipment efficiency when comparing these alternatives. The coefficient of performance, or COP, is energy output divided by energy input. The COP of electric resistance heating is nearly 1.0. This means nearly all of the electrical energy is converted into heat energy. The boiler in the baseline is 87% efficient. So the baseline will require more energy in to produce the same heat energy compared to the electric heater. This does not mean electric heat will cost less than the natural gas boiler in the baseline. Even though the rate ratio is only 2.6, the cost to heat with electricity is still more than the cost to heat with natural gas. In this case, using less energy still costs more. Okay, let's look at another option. In this second alternative, we will replace the existing chillers and natural gas boiler with air-to-water heat pumps. The air-to-water heat pumps would serve the dual duty of producing chilled water for cooling and producing hot water for heating. It allows us to remove the boiler, which reduces the on-site fossil fuel emissions. Of course, the building still needs heat that will come from the heat pump. This heat pump consumes electricity, and the emissions analysis later will tell us how that looks. The economics of this alternative are far different than before. Let's step through this one again. There's no natural gas boiler, so there are fossil fuel savings in red. But the air-to-water heat pumps demand and consume more electricity than the baseline, so that utility cost is higher, and as a result, shown here as a negative cost. The project capital cost exceeds the capital avoidance, our baseline cost. The cumulative cash flow savings, the black line, starts in the negative, but is sloped upward, which means this will pay off over time. It crosses the x-axis at year 5.5. So this could be a good investment. While both the SCR electric heating coil and air-to-water heat pump alternatives use electric heating sources, air-to-water heat pumps use less electricity than SCR electric heating coils in our example building. Compared to electric heat's COP of nearly 1, the gas boiler's 87% efficiency, our design heating COP for the air-to-water heat pump is 2.5. The cooling COP is very close to the COP of the baseline air-cooled chillers. Now, this building is in a mild climate, so our air-to-water heat pumps did not reach their low-temperature operational limit and didn't spend much time operating at temperatures below 47 degrees Fahrenheit, which would derate equipment efficiency. So in this case, with the given utility rate structure and a rate ratio of 2.6, the air-to-water heat pump's annual electricity use is low enough to cost less than the baseline's annual electricity and natural gas use.
Now, let's move on to our second set of scenarios. What if this building were served by a utility company with a high rate ratio, specifically with high electrical demand charges instead? Let's say the electricity consumption charges are a little higher than our low rate ratio, but the electricity peak demand charges are much higher, $30 per kilowatt during summer peak periods and $24 per kilowatt during winter peak periods. The natural gas rate is $1.10 per therm, an increase over the previous utility rate. The rate ratio is now 5.2, indicating a much larger difference between the electrical and gas utility costs. Since our on-peak time is weekdays from 12 p.m. to 7 p.m., the high on-peak demand charges will really add up.
Okay, let's look at the air-to-water heat pump central plant upgrade, but this time using the high rate ratio utility. On the left, you can see the earlier economic analysis with the low rate ratio, where the plant upgrade paid off at year 5.5. Now on the right, you can see our system using this different utility rate. Here's the full-size chart. The dark blue colored bars are greater in size, indicating more electrical energy cost due to higher demand charges. The downward slope of the cumulative cash flow line shows that this investment is not going to pay off. So how can a heat pump upgrade work with a high rate ratio utility like the one Michelle mentioned earlier? Our next alternative is to add thermal storage to the heat pump system. This likely makes the most sense when the utility rate has a high demand charge. This is used to reduce the demand cost by producing ice at night. During the day, when the electrical demand charge is high, we can use the ice to produce chilled water for cooling without heat pump operation. During the heating season, the air-to-water heat pumps provide hot water for heating. There is no fossil fuel boiler. Adding thermal storage dramatically changes the math. In our ice storage schedule, the ice tanks provide cooling from 12 o'clock p.m. to 8 o'clock p.m., mostly during the on-peak hours. The project capital cost in gray does go up to account for the ice tanks and installation. The electrical demand savings is much better now because the presence of thermal storage tanks allows us to shift energy use to off-peak hours. The cumulative cash flow line is sloped upward and shows an investment payback at year 10. Even though the total energy needed with ice storage is comparable to the cooling energy of the air-to-water heat pumps without thermal storage, we use much less electricity to meet the cooling loads during on-peak hours, reducing the overall electrical utility cost. Now, some utilities might offer rebates for specific projects. Thermal energy storage is one that utilities often incentivize because it shifts electrical load from peak to off-peak generation periods, which is better for them too. This green bar accounts for a modest utility rebate to help offset the initial project cost. This helps reduce the total cost in year 1 and moves the payback period forward to year 8. It might get even more lucrative if there is a carbon penalty. This could be a carbon tax imposed by a government or an internal cost of carbon levied by a company on itself. A company could carry an internal cost of carbon to ensure that projects with positive sustainability outcomes are prioritized and chosen, helping the company meet its own sustainability goals. Now, in this hypothetical project, there is a carbon penalty shown in green each year. I've highlighted it for the first 3 years. Now, this is a positive value because it's an avoided cost. The baseline would have emissions from the boiler, but the heat pump and thermal energy storage system will not. This helps improve the payback period now to about 4.5 years. Now, we've seen several factors which can improve operational costs and payback period, including an incentive from the utility and even a CO2 penalty that would be levied on a system with fossil fuel emissions. Utility demand response programs could be another incentive to reduce operational costs. We've looked at several different upgrade paths to reduce emissions. There are a variety of other considerations to think about. It may be undesirable to disturb occupants during an upgrade, so swapping VAV boxes might not be a possibility. Another consideration is heating coil capacity. Existing coils in the air handlers and VAV boxes may be designed for 160 degree Fahrenheit or warmer supply water temperature. The air-to-water heat pumps cannot provide that same temperature. So coils need to be evaluated with a lower heating water temperature. For the VAV reheat coils, there are several options. First, we can implement a dual maximum control sequence to allow milder supply air temperatures when heating with more airflow. Next, we might need to replace reheat coils with ones that have more heat transfer surface area, which usually means more coil rows. For air handler preheat, it might make sense to evaluate air-to-air energy recovery and transfer heat from the exhaust air stream to the incoming outdoor air stream. Depending upon the climate, a preheat coil may still be needed to prevent frosting on the energy recovery device. We recently had an ENL on the topic of air-to-air energy recovery, and I've included that in this program's bibliography. For air-to-water heat pumps, consideration needs to be given to cold weather operation. Remember that heat pump operation and capacity are affected by cold weather. One option could be to keep the natural gas boiler and use it when the air-to-water heat pumps cannot operate or cannot provide enough hot water. Alternatively, an electric boiler could be provided to perform the same task. Or we might need to look at other solutions like a storage source heat pump system. System selection is also affected by simultaneous operation, so it makes sense to evaluate and understand the simultaneous demand for chilled and hot water to properly select components. We recently published an engineer's newsletter on the topic of heating with lower temperature hot water. You'll find that in today's program bibliography. Now, what about the electrical infrastructure?
One consideration that can make or break a project financially is the electrical infrastructure requirements. While it's important to consider this in any project, with electrification of heating projects, the increase in electricity use means many projects will require some degree of electrical upgrade. In a retrofit, this means comparing the electrical needs of existing equipment versus new equipment. Is the new equipment the same voltage as the old equipment? Does the new equipment require more or less amperage? The ultimate question is how far down the electrical chain you need to make upgrades to have enough power for the new equipment. In general, the farther down the line you go, the more expensive the upgrade, and upgrades may compound on one another. A circuit breaker, while likely the least expensive component to replace, can still cost thousands of dollars. It also requires space in the distribution panel to fit the breaker. If the distribution panel needs to be upgraded, you need to consider upgrading incoming service lines and equipment lead times. A transformer might need to be upgraded by the utility, which you could be responsible to pay for. For projects where the increase in power is extreme, the utility company may even need to upgrade the infrastructure to the entire neighborhood. Replacing wire can be extremely expensive, which could be required at one or more sections in the chain of the equipment. Because of how costly upgrades can get, fully electrifying heating might not make sense financially for all projects. Instead, partially electrifying, that is, only replacing some non-electric heating equipment with electrified heating equipment, could be a step towards electrification without significant electrical upgrades. It's important to contact a local electrical engineering firm to conduct a power study to determine what, if any, electrical upgrades are needed, how to upgrade according to electrical codes, and what associated costs are in your area. In our example scenario, the existing equipment are two 140-ton Trane RTAC air-cooled chillers, ordered in 2006. The rated voltage is 460 volts. The minimum circuit ampacity, or MCA, is 288 amps. This amperage sets the minimum size of wiring required for the circuit to avoid overheating. The maximum overcurrent protection, MOP, is 400 amps. The MOP is the maximum average to properly protect equipment and is used to size fuses and breakers. The new equipment are two 140-ton Trane ACX air-to-water heat pumps. The rated voltage is the same as our existing equipment, and because we do not have a pump package included and are using electrically commutated fans, the MCA allows us to use the same size wiring as the old equipments. The MOP is actually lower in this case, 350 amps compared to 400. To mitigate the change in MOP, we have a few options. We could swap out the 400 amp breaker for a 350 amp breaker, put a 350 amp fuse disconnect between the unit and the breaker, or if the existing 400 amp breaker has dip switches that allow for a manual maximum current setting, to simply change the trip setting on the dip switches to 350 amps. In our example, we are assuming that we have an existing 400 amp circuit breaker with dip switches capable of being set to 350 amps, so no electrical upgrade is needed.
Let's next look at the emissions aspect of these alternatives. Before we actually show emissions, I want to explain how we chose the rates used to calculate emissions for this analysis. This chart shows the energy usage in each alternative. I've converted the natural gas units to kilowatt hours so that all energy can share an axis in the chart. Note that although Eric presented more alternatives than the number of bars you see here, those were based on only these 4 different HVAC systems. The other variations only had financial factors changing. Energy consumption, and therefore emissions, are the same between financial alternatives 2 and 2B, and the same between alternatives 3, 4, and 5. The color of the bars show which emissions factor, or emissions rate, that we apply to the energy consumption to calculate the associated emissions. Natural gas is easy. Fossil fuel emissions factors are relatively constant, so we only need to use one factor for any fossil fuel consumption. For electricity, we need to use some of the concepts we discussed in the first part of this ENL. The baseline electricity is what the grid has historically seen, so we'll use the total output emissions rate. However, the additional electricity consumption in excess of the baseline amount is new load on the grid, and therefore much more likely to contribute to a need for non-baseload resources during peaks. So for this additional consumption, we'll use the non-baseload or marginal emissions factor. The exception is the alternative that includes ice storage. This system will be consuming less electricity during peak times and more electricity during non-peak times. This load shifting reduces the utility's need for non-baseload generation resources, so a total output emissions rate is more appropriate. Similar to how we compared how different utility rates can impact project outcomes, we're also going to compare outcomes using 2 different electricity emissions rates, one from a high emissions intensity or dirty grid, and one from a low emissions intensity or cleaner grid. This chart shows the annual CO2e emissions in metric tons by alternative for the dirtier grid. Keep in mind that the baseline emissions include both electricity and natural gas emissions, while each electrified alternative includes only electricity emissions. Notice that our first alternative, the electrified VAV option, had so much more energy consumption than the baseline that the additional electricity emissions significantly outpaced the natural gas emission savings, resulting in much higher total emissions. Alternative 2, with air-to-water heat pumps, also had enough additional electricity consumption to outpace the natural gas emission savings from the baseline, but not by quite as much. The solution that was presented in alternatives 3, 4, and 5, the air-to-water heat pumps with ice storage, shows a lower emissions impact than any other scenario. As this grid decarbonizes with less emissions-intensive electricity generation sources, the emissions of these alternatives will decrease. The lighter green bars show the same alternatives on a cleaner grid. Again, the electrified VAV alternative still produces more emissions than our baseline system, but the air-to-water heat pump alternatives do have fewer emissions. Let's review and summarize. This analysis showed how an existing building could be evaluated for electrification. Let's take a look at a summary of the payback and emissions. Recall that we evaluated two utility rates, one with a low rate ratio and another with a high rate ratio. And the emissions analysis looked at two grids, one which is dirtier with more fossil fuel generation, and another with cleaner electricity sources. First, we established a baseline with like-for-like equipment for comparison. The first alternative, with electrified VAV boxes and a low rate ratio, did not pay off. It also resulted in higher emissions on both the dirty and clean grid. Next, replacing the chiller and boiler with air-to-water heat pumps with the same utility rate did pay off in alternative 2, about 5.5 years. However, with a higher rate ratio driven by high demand costs, it no longer paid off. This solution resulted in higher emissions on a dirty grid, but slightly lower emissions on a clean grid. So, in alternative 3, we looked at adding thermal energy storage. This paid off in about 10 years and resulted in lower emissions on both the dirty and clean grid. Adding a utility incentive brought the payback forward to 8 years. Finally, in alternative 5, we looked at how a CO2 penalty would impact the payback period. In our example, it brought the payback farther forward to 4.5 years. So there are a myriad of options to consider when evaluating electrification projects. Utility costs, incentives, and penalties can have a substantial impact on the payback period.
Thanks, Emma. Wow, that was a lot of great information. Emma discussed how the electrical grid operates to help us understand electrical rates and emission factors, along with 3 characteristics. Firmness describes the extent of which generation can be predicted in advance. Dispatchability refers to how quickly and easily an electrical generation resources can be brought online. Finally, emissions intensity describes how clean or dirty the electricity sources are. For example, coal has a very high emissions intensity compared to wind or solar. Different grid subregions have different emissions intensity because they have varying power generation sources. Michelle discussed the rate ratio, the ratio between the cost of electricity and natural gas. A low rate ratio indicates a small difference in the cost of electricity and natural gas, whereas a high rate ratio indicates a large difference, often meaning the cost of the electricity is high compared to natural gas. The rate ratio can be used to help make preliminary electrification decisions. A building with a low rate ratio is often a great place to start when considering electrifying equipment because the cost of electricity is usually lower than a location where a high rate ratio. Michelle also discussed different types of electrical rates ranging from flat, time of use, stepped, seasonal, and ratchet rates. The team reviewed an example to illustrate how this all works together. Different electrification options were evaluated with different utility rates to show different payback periods. Now, utility rates could certainly impact the decisions made by the designers. And finally, we saw how these different alternatives produce different emission outcomes based upon whether the grid is cleaner or dirtier. As always, the bibliography included in your handout provides more information on where to find many resources related to today's topic, all free and available 24/7. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. And finally, for those of you viewing in person, please ask your local host about upcoming details around Engineers Newsletter Live programs, or check them out at trane.com/ENL. And also check out our new podcast, Cool Air Hot Takes, launched earlier this year, as an entertaining way to keeping up with the industry news and trends. Thanks for joining us today. We look forward to seeing you next time.